Right, so today in Algebra 2, we're going to look at Chapter 7, Trigonometric Functions. Our Chapter 7 essential question, how are trig functions used to solve real-world problems? The 7.1 essential question, how can ratios of lengths of sides within right triangles help determine other lengths and angle measures in right triangles? After today's lesson, you should be able to use trig functions. The three sides of a right triangle are referred to as the hypotenuse and two legs. So the hypotenuse and two legs. The Greek letter read theta is often used to represent an acute angle in a right triangle. Angle theta is used as an abbreviation for angle with measure theta. So in this picture, we have our right triangle. We have angle theta up here marked. We have the hypotenuse. From angle theta, we have the opposite side and the adjacent side. And again, that's if I'm standing at this angle, adjacent touches that angle, opposite is across, hypotenuse is always across from my right angle. So we're going to recall from geometry, SOHCAHTOA, our sine, cosine, and tangent ratios. So remember that the sine of theta is equal to the opposite over the hypotenuse. So we should have an E there. The cosine of theta is equal to the adjacent over the hypotenuse, and the tangent of theta is equal to the opposite side over the adjacent side. Now we're going to talk about the reciprocal trig functions. Okay, so we don't talk about these in geometry. So the reciprocal trig functions of the angle theta are formed by exchanging the terms in each ratio. So if I were to take sine and flip it and get hypotenuse over opposite, that is referred to as the cosecant of theta. The secant is the cosine flipped, so that's hypotenuse over adjacent, and cotangent is the tangent flipped, adjacent over opposite. So let's look at some examples. This is given the right triangle below. Write the 6 trig ratios for the given angle with measure theta. So if I start out with the sine of theta, and again, remember from geometry, I'm standing here, okay? You can, if it helps you to label them at the beginning, this is opposite, this is adjacent, this is hypotenuse. So the sine of theta is the opposite side, 21 over the hypotenuse, 29. The cosine of theta, my adjacent side, 20 over hypotenuse, 29. My tangent of theta is the opposite, 21 over the adjacent, 20. So now I want the cosecant. The cosecant just means I flip the sign, so that's 29 over 21. The secant of theta, I flip the cosine, so 29 over 20. And the cotangent of theta is 20 over 21 because it is adjacent over opposite. So example number 2 says using one trig ratio that the tangent of theta is 15 over 8. What are the other 5 trig ratios? If it helps, we can draw that right triangle. Again, it doesn't matter which angle I call theta. I'll just call this one up here theta. The tangent, remember, is opposite. So opposite was 15, adjacent 8. I could do Pythagorean theorem to find my hypotenuse. So 8 squared plus 15 squared equals h squared. Or we could recognize from from geometry again that this is one of our triples. We don't recognize that. We'll just keep going. 64 plus 225 equals h squared. So I get 289 is equal to h squared. So h is equal to 17. So now I want the sine of theta, the cosine of theta. I want the cosecant of theta, the secant of theta, the cotangent of theta. The cotangent, I can go ahead and get, I know that's going to be 8 over 15. The sine of theta, and if I'm standing up here at angle theta, sine is opposite over adjacent, so 15 over 17, which means that the cosecant is 17 over 15. The cosine of theta, 8 over 17, so the secant is the hypotenuse over the adjacent, 17 over 8. So example number 3, again, this would look like something that we did in geometry, word problems with our trig ratios. A fire truck has an 84-foot ladder extended against a building, forming a 55-degree angle at the top of the fire truck. The truck is 8 feet tall, so that tells me from here to here is 8. The firefighters are trying to reach a window that is 75 feet above the ground. will they be able to reach the window using the ladder set at this angle? Okay. So again, this is my right triangle that I have. I'm looking to see what is this height, right? The total height from the ground all the way up, right? So I could say that the sine of 55 is equal to, because this is my opposite side, this is my hypotenuse, so the sine of 55 is equal to, we're just going to call that x over 84. Cross multiply, 84 times the sine of 55 is equal to x. When I plug this in, I get x is approximately 68.8. But now remember that my fire truck is 8 feet tall, so I'm going to do 68.8 plus 8. And I'm going to find out that this window is approximately 76.8 feet tall. I'm trying to reach, my ladder will reach approximately 76.8 feet up. I'm trying to reach a window that is 75 feet above the ground. So yes, the ladder will reach. Number 4, the sun shines at a 60-degree angle to the ground. How long is the shadow cast by a 20-foot tall flagpole? So again, here's my sun, here's my flag, it's casting a shadow. Remember from geometry, we said that the shadow is always on the ground. We're looking for the length of the shadow, so that's my x. The flagpole is 20 feet tall. The sun shines at an angle 60 degrees to the ground. Here's my ground, 60 degrees. So again, if I'm standing right here, I have the opposite and the adjacent, so that's tangent. So the tangent of 60 is equal to 20 over x. Cross multiply, x times the tangent of 60 equals 20. This time I have to divide by the tangent of 60 to get my x by itself. So I get x is approximately 11.5 feet tall. So now we're going to do some more review from geometry. So our special right triangles are 45, 45, 90, and our 30, 60, 90. So we'll start out with the 45, 45, 90. So in a 45, 45, 90, remember that both of my legs are the same. So if this leg is 1 and this one is 1, my hypotenuse is the leg times the square root of 2. So remember your hypotenuse is your leg times the square root of 2. 30, 60, 90, so we'll call this 30 up here, this 60 down here. Remember that my short leg is across from 30, my long leg is across from 60, and then my hypotenuse is always across from 90. So if we call our short leg 1, our long leg is our short leg times the square root of 3. So long leg equals short leg times the square root of 3. Our hypotenuse is our short leg times 2. So this would be 2 here. So number 5, triangle MNO is a 45, 45, 90 triangle with side length OM equals 2. What are the 6 trig ratios for angle N with measure theta? Okay. So they tell me that OM is a side, not a hypotenuse. So I'm going to say this is O, this is M, this is N. So this is 45. O to M, they told me it was 2. Okay. Since I know that it's a 45, 45, 90, I automatically know my other leg is 2, and my hypotenuse is my leg times the square root of 2. So our 6 trig ratios. So the sine of theta is going to equal 2 over 2 square roots of 2. I cannot have that radical in the denominator, so remember we multiply top and bottom by that radical. These 2's cancel, so on top I have the square root of 2 over the square root of 2 times the square root of 2 is 2. The cosine of theta, remember that these are both angles are 45, so since they are the same angle, the sine and the cosine will be the same, so the square root of 2 over 2. The tangent of theta is equal to opposite over adjacent, 2 over 2, which is equal to 1. So now I want my opposites, my reciprocals. So the cosecant of theta, I'm going to go back to the very beginning where I had 2 over 2 square roots of 2. If I flip that, I get 2 square roots of 2 over 2. Those 2's cancel. I'm just left with the square root of 2. The secant is going to be the same, square root of 2. The cotangent, if I flip 1, I still get 1. So now we're going to do that again with the 30, 60, 90 triangle. So we're going to draw ourselves a 30, 60, 90. So this is my 30 up here. This is my 60. This is LK, so measure J is 30, so this is J. LK is a side, so this has to be L, and this K. L to K is 4. So now, because I know my short side, I know my long side is 4 square roots of 3. My hypotenuse is my short side times 2, so 4 times 2 is 8. So again, now I can find all these. The sine of theta is equal to 4 over 8, which is reduced to 1/2. The cosine of theta, again, and theta here is our 30 degrees. The cosine is 4 square roots of 3 over 8. The 4 and the 8 reduce, so that becomes the square root of 3 over 2. The tangent of theta is 4 over 4 square roots of 3. My 4's cancel, but I need to rationalize that denominator, so I end up with the square root of 3 over 3. So now we're going to find the reciprocals. So the cosecant of theta, I flip the sign, so 2 over 1 becomes 2. The secant of theta, again, I'm going to go back and I'm going to, before I, reduced or anything, but again, so I would have 2 over the square root of 3. I can't have that radical, so rationalize, so I get 2 square roots of 3 over 3. And my cotangent of theta, this one I'm going to go back before I rationalize the denominator. So I would have had 4 square roots of 3 over 4. My 4 still cancels, so I'm left with the square root of 3. Number 7, the length of the hypotenuse in a 45, 45, 90 triangle is 5 square roots of 2. So again, I know it's a 45, 45, 90, so my hypotenuse is 5 square roots of 2. What are the sine and the secant ratios for a 45-degree angle? I need to find my legs. Remember that my hypotenuse is equal to my leg times the square root of 2. So if my hypotenuse is 5 times the square root of 2, that means that each of my legs are 5. So this is 5 and this is 5. It just asked me for the sine. So the sine of theta here is equal to 5 over 5 square roots of 2. My 5's cancel, rationalize my denominator, so I end up with the square root of 2 over 2. They asked me for the secant. The secant would be the opposite of the cosine, but again, I remember that sine and cosine will be the same in a 45, 45, 90. So I would go back to at the very beginning before I rationalize this, and I would have 5 square roots of 2 over 5. My 5's cancel, so it's just the square root of 2. So now we're going to talk about what's called an identity. An identity is an equation that is true for all values of the variable for which expressions in the equation are defined. We have seen that some trig functions include ratios that are reciprocals. We're going to confirm that the equation sine of theta equals 1 divided by the cosine of theta is true algebraically. So I know that the sine of theta is equal to the opposite over the hypotenuse. I know that the cosecant of theta is equal to the hypotenuse over the opposite. So I'm just going to rewrite this. Sine of theta equals 1 over, instead of cosecant, I'm going to put the hypotenuse over the opposite. I don't want a fraction in the denominator, so I'm going to flip and multiply top and bottom by opposite over hypotenuse. So here everything cancels, and I'm left with the sine of theta equals the opposite side over the hypotenuse, which is in fact true. Now we're going to talk about the Greek letters alpha and beta. They're often used to represent angles in trig. So here we have this picture, and it just says compare the sine and the cosine for alpha and beta. So first let's talk a little bit about alpha and beta. If I'm in a right triangle, then I know that alpha and beta are complementary. I know that those two angles together have to equal 90. So I could say that alpha plus beta equals 90 degrees, which means alpha equals 90 minus beta, and beta equals 90 minus alpha. So if I compare the sine of alpha, the sine of alpha would be xz over yz. The cosine of alpha is going to equal xy over yz. Now let's look at the sine of beta. The sine of beta is xy over yz. The cosine of beta is equal to xz over yz. So what do I notice? I notice here that the sine of alpha is equal to the cosine of beta. The cosine of alpha is equal to the sine of beta. We discovered that last year in geometry as well when we did SOHCAHTOA. But if alpha and beta are complementary, then the sine of one angle equals the cosine of the other angle, and vice versa. Right, so now we're going to say if beta equals 90 minus alpha, then the sine of alpha equals the cosine of beta, and the cosine of alpha equals sine of beta. That's what we just talked about. The trig functions for the complement of an angle is called a cofunction. So these are the cofunction identities for sine and cosine. Okay? So we could say that the sine of alpha, the sine of theta, we could just call that any angle theta, is equal to the cosine of 90 minus theta. The cosine of theta is equal to the sine of 90 minus theta. Okay. So our next example, triangle DEF has a right angle, F. Angle D is alpha, angle E is beta. If sine of alpha is 8 over 17, and cosine of alpha is 15 over 17, find the sine of beta. Since I know that the sine of beta equals the cosine of alpha, I don't even have to look at my triangle. I know that the sine of beta is equal to 15 over 17 because that equals the cosine of alpha. And find the cosine of beta. So the cosine of beta is going to equal the sine of alpha, which is going to be 8 over 17. Okay. Number 9, what are the cofunction identities for tangent and cotangent? All right, so let's do this again. This is alpha, this is beta. We'll call this x, y, and z. So let's look at the tangent of alpha is equal to zy over xz. The tangent of beta is equal to xz over zy. The cotangent of alpha equals xz over zy. The cotangent of beta equals zy over xz. And so I notice that the tangent of alpha equals the cotangent of beta. The tangent of beta equals the cotangent of alpha. So I could therefore say my cofunction identities, the tangent of alpha equals the cotangent of 90 minus theta. The cotangent of theta equals the tangent of 90 minus theta. And we'll do some more work with these later on in this chapter. But that is our very first section, 7.1. A lot of review from geometry and a little bit of new things in there too.